A green hydrogen project gets announced. The numbers look solid. The technology works. The funding is lined up. On paper, it should move forward. And yet, months later, sometimes years later, it disappears. No headlines, no explanation, just silence. The assumption is always the same. Maybe the technology wasn't ready. Maybe the costs were too high. Maybe the market wasn't there yet. But those explanations miss something far more uncomfortable. The real problem often has nothing to do with hydrogen itself. It has to do with where that hydrogen was supposed to exist. There is a map behind every energy system. Not a political map, not a map of countries or borders, but a physical map of sunlight, wind, water, infrastructure, and demand. This map determines how energy flows, where it can be generated, how it can be moved, and whether it can ever become economically viable. And in green hydrogen, this map is not just important, it is everything. Because hydrogen does not create energy, it consumes it. It sits at the end of a chain that begins with electricity. And that electricity must come from somewhere specific, at a specific time, at a specific cost. Take two identical hydrogen plants, same electrolyzer technology, same 50 megawatt capacity, same engineering design. Build one in southern Spain and build the other in a coastal region of Namibia. On paper, they look identical. In reality, they are completely different systems. The Spanish plant may face grid congestion, fluctuating electricity prices, and limited hours of renewable availability. The Namibian plant, sitting under some of the most consistent solar irradiation on the planet, may operate far more steadily with fewer interruptions. The difference is not the hydrogen, it is the map. This is where most discussions around green hydrogen begin to break down. They focus on the cost of electrolyzers, the efficiency of the stack, or the promise of falling renewable prices. All of that matters, but it exists downstream of a much more fundamental constraint: utilization. How many hours per year can that plant actually run? Because a hydrogen plant that runs 7,000 hours per year behaves very differently from one that runs 3,500. The capital cost does not change, the equipment does not change, but the output is cut in half. And when output drops, cost per kilogram rises sharply. The economics don't degrade slowly, they collapse. Now, layer in the rest of the map: water availability. Hydrogen production requires water, and while the volumes may seem modest compared to large industrial processes, the reality becomes more complex when you consider purification, cooling, and local conditions. In arid regions, water must often be desalinated or transported, adding cost and complexity. In water-rich regions, that constraint may disappear entirely. Again, same plant, different map, different outcome. Then comes distance. Hydrogen is not easy to move. It is a low-density molecule that requires compression, liquefaction, or conversion into derivatives like ammonia to be transported at scale. Every kilometer between production and demand adds cost, infrastructure requirements, and potential losses. A plant built far from industrial demand centers may look viable in isolation, but once transport is included, the economics shift. Suddenly, location is no longer a detail, it becomes the defining variable. And yet, despite all of this, projects continue to be announced in locations that struggle with exactly these constraints. Regions with limited renewable capacity, congested grids, high electricity prices, or weak infrastructure. Not because developers don't understand the map, but because other forces are at play. Policy incentives, political visibility, proximity to existing industry, or the desire to lead in a new technology. These forces push projects into places that make sense on paper, but not within the deeper energy system. This is where the hidden tension begins, because the global conversation around green hydrogen suggests a uniform transition. As if hydrogen can be scaled anywhere as long as the technology improves and the investment continues. But the map does not allow uniformity. It creates winners and losers before the race even begins. Some regions have abundant renewable resources, available land, access to water, and proximity to export routes. Others do not. And no amount of technological improvement can fully erase those differences. If you look closely, you begin to see a pattern forming. The most promising large-scale hydrogen projects are not always located in the most industrialized regions. They are appearing in places with exceptional renewable conditions: parts of Australia, the Middle East, North Africa, coastal regions of Latin America. These are locations where the map aligns, where high solar or wind capacity factors can drive high utilization, where land is available, where export infrastructure can be developed with scale in mind. But this creates a second layer of complexity. Because producing hydrogen in one place and consuming it in another introduces a new system. Shipping, conversion, storage, reconversion. Each step adds cost, inefficiency, and risk. The map may favor production in one region, but demand remains concentrated elsewhere, and bridging that gap is not trivial. It requires building an entirely new global supply chain, one that does not yet exist at the scale required. This is where many projects encounter what can only be described as system stress. Not a failure of technology, but a failure of alignment. The renewable resource is strong, but the infrastructure is weak. The demand is real, but it is too far away. The policy support exists, but the grid cannot deliver the required power. Each of these misalignments reduces utilization, increases cost, or delays timelines. And when multiple misalignments occur at once, projects stall. Not publicly, not dramatically, but quietly in the background, as timelines slip and economics no longer hold. From a financing perspective, this becomes critical, because investors are not evaluating hydrogen in isolation. They are evaluating the entire system around it. Can the plant run consistently? Is the electricity supply reliable and affordable? Is there secured demand? Can the product be delivered without excessive cost? If any of these answers are uncertain, the project becomes difficult to finance. And this is where many projects fail long before construction ever begins. The map, in this sense, becomes a filter. It determines which projects can move forward and which ones cannot. Not based on ambition, but on alignment. And this is why the conversation around green hydrogen often feels disconnected from reality. Because it focuses on what is technically possible rather than what is systemically viable. Now imagine how this evolves over time. As more projects are announced, competition for the best locations increases. Regions with strong renewable resources and export potential become hotspots. Infrastructure begins to cluster: ports, pipelines, storage facilities. These clusters may become the true centers of the hydrogen economy, not because they were planned that way, but because the map made them inevitable. At the same time, projects in less favorable locations face increasing pressure. Higher costs, lower utilization, more complex logistics. Some may adapt by shifting to niche applications or integrating with local systems. Others may not survive at all. And this creates a divergence in the hydrogen landscape, a world where a small number of regions dominate production, while others struggle to participate meaningfully. This raises a deeper question. Is green hydrogen a global solution or a geographically constrained one? The answer is not simple. Hydrogen can be produced almost anywhere, but not everywhere equally. And the difference between possible and competitive is where the entire system is decided. This is also where the narrative begins to shift. Because the future of hydrogen is not just about scaling technology. It is about understanding and working with the map, designing projects that align with physical realities rather than trying to overcome them. Accepting that some regions will lead while others will follow or adapt in different ways. And this is the part that is rarely discussed. Not because it is unimportant, but because it challenges the idea of a uniform energy transition. It introduces constraints, trade-offs, and difficult decisions. It forces a recognition that not every project will succeed, and that success is often determined long before the first piece of equipment is installed. This is exactly where a deeper understanding of the system becomes critical. Not just for engineers, but for developers, investors, and policymakers. Because the decisions being made today are not just about building plants. They're about positioning within a global energy map that will shape the next several decades. And once you see that map, the entire conversation around green hydrogen changes. It is no longer about whether the technology works, it is about where it works, how it connects, and whether the system around it can support it under real-world conditions. This is exactly the layer most people miss. The part of the system that determines whether a project moves from concept to reality. If you're working in hydrogen, investing in it, or trying to understand where this industry is actually going, this is where the real insight sits. Not in the headlines, but in the structure underneath them. If you want to go deeper into how these systems actually come together, including the economics, the constraints, and the real-world execution challenges, you can explore that further through H2 Hub by Renee Energy, linked in the description below. Because the future of green hydrogen is not just being built in factories. It is being shaped by the map, and the map is far more selective than most people realize.